Okay, so this is the Physics 2 session. So I'm just going to start and we'll take a look at the homework that is due today. Okay, so we've covered Kirchhoff's law, and now we enter magnetism and B fields. So before we start the homework, let me just give a brief description about the B field, which might clarify any confusion and will also possibly help with the homework. So let's just get started with that. So what the B field is, so we're used to the electric field, symbolized by capital E. Now we're going to have a B field, which is given by magnetism. And so the B field works a little differently in respects to where we have to take, with E field, we just had the constant lines like these, constant radiating lines from a charge, say charge Q. Let's say this is positive. Let's say this is negative charge here. And so for these, we just had charges leaving, coming in. And you get this sort of spiral, spider-like thing, which you've seen in your lab that you did, where you had the conducting paper, you take the charge, you put it on the paper via the pin, the two thumbtacks, and then you can see this type of spiral draw out. Now the B field is not that simple, but the B field, you have to take into account vectors. And so at this point, I'm assuming everyone's already taken at least, algebra 2, 3, or sorry, calculus 2 or 3, and obviously physics 1. So you're familiar with vectors. So let's just let's do what the different types of vectors are. So we have here vector A cross B. And this is essentially AB sine theta. So if we have something like this, X, Y, Z, let's say you have vector A going this way, vector B going this way, vector theta, so here, correct, you take the sine of theta. And so what this will essentially do is give you a third vector, which is perpendicular to A and B. So you're going to get a third vector. We'll do it with this color, it's purple, the blue. Forgive bad drawing, something like that. And the angle between this is going to be 90 degrees, and the angle between this is going to be 90 degrees. So that's what you get from a cross product. Now let's do a dot product, a dot B, and I'm showing what vectors are and how to do vector manipulation, because that's how you're going to be crossing E fields, B fields, the velocity, as we saw in class. So you have to know how to cross vectors, because if you don't cross them properly, then you're going to have troubles. So you have here dot B, and this is the dot product, and this is just AB cosine theta. Cosine of theta. Okay, so that's simple dot products and cross products with vectors, and that you will also need to cross E fields, B fields, velocities. Now let's start on what magnetism is in pipes or like wires, because when we did chargers, oh hey, there's a here. Hi. Okay. So do you have any questions? I'm just going to do like a basic review of what magnetism is, because B fields or magnetic fields are different from E fields, right? In like different senses. So I was just going to do that.
Yeah.
But if you guys have actual questions, then I can do those too, or I can just do this. It's up to you. Okay, so I'll do this, and then I'll do that for about like 10 minutes. And then if you have questions, you can do that, or
Yeah.
whatever. Okay, so now I'm not going to talk to a computer. I'll talk to you. Yeah. Alright. Okay, so what I was explaining is, you guys have all taken physics 1, obviously, and then calculus. So you know that A cross B is the sign of everything, and A dot B is, so you know dot products and cross products, right? Okay, great. So now, let's see this. Okay. And so in E fields, they work a little differently than, B fields work differently than E fields, right? B fields are magnetic fields, which are a little different. So did you guys do the lab yet, where you have a wire,
No.
and then you have a compass? No? Okay, well, you'll get to that. So the way B fields work is that, so the way E fields work is that you have a charge, you have a minus charge, and then you see the lines radiating like this, like this, blah, 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 right? That's how E fields work. B fields work a little different. So for B fields, let's just take a parallel wire. Let's just take two wires in which you have current, because obviously you'll have current flowing through the wires. And so the next lab, or maybe the lab after that, you'll witness what I'm about to show in drawing, okay? So you have two wires, here and here. Now let's say the current in both of these are flowing to the right, okay? So you have current flowing this way, and you have current flowing this way. So in B fields, the way the forces, so B fields have attractive forces, right? It's like magnets, right? Magnets have attractive forces. So forces in B fields will be going, so if you have the current in two wires in the same direction, the force will be attractive. Okay, so like this. Where the blue, the arrows are the force, the attractive force. Okay? So it's as if you put two ends of the magnet together and they come really close. And boom, they connect. That because the forces between them are attractive. Okay? Now if you have something like this, where the current's going in one direction to the right and the current's going in the other direction, then you would have something like this. So the forces are going to repel each other. And you can witness this when you put the two north ends of the magnet together, or the two south ends of the magnet together. That you have to put a lot of force and really low temperatures to bring them together. No matter how hard you try, they're always going to bounce off, right? That's because of this. The currents are different, the poles are different, so they're going in opposite directions. Okay, that's the force. So let's just do this. Yeah. So the second thing. The equation of the force is F equals QV cross B, where B is your magnetic field. So F equals Q, which is the charge of whatever you have, V, the velocity, cross B. And remember, you have to put a vector because B is a vector. The B field is a vector. It points in a certain direction, right? So like if you have a plane like this, X, Y, Z, either your B field can be going into the plane, it can be coming out of the plane, whatever, right? It will have a vector. It will have a direction and a magnitude. Okay? So that's why we have to get to know how to do cross products and dot products for this specific reason, because E fields and B fields and velocities are all vectors. So you'll have to take the right hand rule. So do you have any problem with the right-hand rule? It's very straightforward for the most part. Yeah? Right, so no problem with that. Okay. So that's the formula for the force. For the force for V field. Right. Now, you can relate the V field and the electric field from this equation, where B or E over B is equal to V, where V is the velocity. Right? And so you have a vector divided by vector cancel out. Now, this is where if you have this relationship, this ratio between the E field and the B field, there will be zero velocity on the particle in there. There will be no force on the particle with this velocity. So let's say let me give you an example. Write that down first. Okay, so let me give you an example. And this is an example from my old exam. Okay, so I can give you an example. Just find it. Okay, so let me explain this in a little bit. That's weird. I can't seem to find it. Well, okay. Can't find it. But anyways, so remember you saw in class where you had like, can I get rid of this? Okay. Remember in class you saw that like, okay, let's say you have, no, just give me this. Let's see. Okay, so let's say the V field is coming out of the board. Okay. Right, and then let's say you have a particle entering the YZ plane. Okay. So YZ plane. You have a particle entering like this. Okay, with some velocity. Okay, and then you have obviously the E field. Okay, let's say you don't know what the E field is. Okay, so you know that, okay, if you have the velocity coming in, you do V cross B, and then you can find out which way the force goes, right, from the equation V equals Q, or F equals QV cross B. Right? So you do V cross B.
Okay.
So if the particle.
Where does the V go?
B comes out of
out
the
of
X,
B?
Y.
Oh.
Yeah, so remember, whenever you take your exams or quizzes or whatever, if you see something like this, okay, that means out. If you see something like this, that means in. And do you know why they use it like this?
Arrow.
It's an arrow. So if you ever look at an arrow, the back always has this cross X for the wind, and the front is a tip. So it's like as if you're seeing an arrow coming at you, you just see a tip. But if you see an arrow going away from you, you see the cross in the back. So that's how they did this. Okay? So you do the V cross V, and you find out that the force will go this way. So if the particle enters, and it takes always a radial curve. It doesn't just drop, right? It goes and, okay? It'll go something like this. That way, okay? But let's say that you want this particle to go straight through the V form, okay? So they say, okay, what direction does the E field have to be in order for it to go straight through? That's where you would use the E over B equals V. Okay, so then I can't find the example. It's better explained in there. But yeah, so they ask you that which direction would the E field have to go in, and if you want this particle to have no force, then you would use EB equals V. And you have your velocity, you have your B field, you can find your E field. And all you need to do is find the direction. Let me see. I don't know why I can't find it. It's kind of annoying. Because if I could show you the drawing, it would make so much more sense. Where's my phone? Was it on this one? You can find any questions you have, like if you want to look through your notes or anything like that.
I have a question on checkpoint.
Checkpoint?
Yeah.
Okay. Let me see. Okay. Number 4.
Number 3.
Compares. Okay. Okay, fine. So let's try that. I'll give it back. Okay. You just put one for all of them.
Oh. You want? I put one for all your students. Just random understanding. Oh, you did explain.
Okay. So here you have F, right? Or sorry, you have V, right? And you know that it goes down. So your F goes this way. So if it's V cross B, it goes that way. All right, so it should be out of the page, is that right?
Yes.
Yes, okay. And over
Wait,
here,
where does the F go?
right here. So the direction, the path that it follows is F. So this might help. Okay? And you have a center, let's just say a center of a circle here, and let's just say center of a circle here. Whatever, it doesn't really matter. Okay, so you know your velocity initially comes in this way, right? And so you follow the curvature of the particle. And we always know that the particle won't go straight. It's not going to go, right? It's always going to take a curved path. So if you follow it like this, right, let's suppose that this was an infinite field and it didn't change chambers. Okay, so just going like this. Your force is in this direction because that's the way it's going. Okay, so the direction of motion, once it enters the chamber, or the V field, is the direction of the force. So your velocity, so your force goes that way. Your velocity comes in this way because you come in from here. And so you know the general direction of your force is to the right. So you go like right, velocity, V field. V field comes out of the page. Where's the black? Oh. So your V field comes out of the page. It's the same thing once you cross this chamber. You have a force, let's just say your force is generally going up, right? Because it goes up. So your force goes up, but your velocity comes in like this, right? Because now this, in this direction, is where you entered this chamber. Okay? When you entered this chamber, you came in this direction. But when you entered this chamber, you came in this direction. So you have a force this way and a velocity this way, so V field goes into the page. Okay? And now, so to find, what was I asking for the magnitude of the V field?
Yeah.
Okay. Let's see. I would say, given on the way that it's drawn, okay, I would think that they don't give me force or anything, do they?
Do you look at how big the curve is made?
Yeah. So if I'm just trying to remember, if it has a really big curve, okay.
Use the equation R equals mv over qv.
What was
So
it?
if R is bigger,
R equals to
mv over qv.
QV.
Yeah.
So the V's cancel out?
qb.
Oh,
Negative, yeah.
okay.
So if R is bigger,
Then B has to be smaller. Okay. And now let me make logical sense of that. Okay. I was about to say that this is stronger. Okay. If you have a field, right? Let's say let's use Earth as an example. Okay. If you essentially what the B field is, it's like a force. It's attracting you to the center, correct? That's why it goes in this radial path because you go towards the center. Right. So if you have the Earth, now let's just use this as an example in order to understand what R, or like how big the radius will change based on that. Right? Now in the drawing, it's very clear. This one has a very much bigger curve than the first one. My drawing is really bad.
what just happened?
That was yeah, so the Earth, okay, it's essentially doing the same thing. If you're closer to the Earth, if you're further away from the Earth, you're going to have a bigger curvature, right? So there's less of a field. But if you're closer to the Earth, it's going to be a smaller curvature. It's going to pull you in faster and harder, right? So that's why whenever they shoot satellites into space, the biggest problem is when they're when they just pass the atmosphere to where Earth's gravity holds everything in, they have to keep that force strong enough in order to get out of that field and then enter orbit. Otherwise, it'll just pull you back in. That's why whenever shuttles re-enter space, they have to enter the field at at the exact moment in order to get back into Earth's normal orbit. Otherwise, they can shoot off into space. And at that point, they won't be able to enter the orbit again. They're going to be flying off into space. So you can sort of relate that to this, and then obviously use the equation, right? If you know your V is constant, B, if it becomes really small, this essentially if V is really small, this gets higher, right? And if V gets really big, then this goes to 0. So then your radius will be really, So use that. So chamber 2 in magnitude will have the weaker B field, and chamber 1 will have the stronger B field. How come I didn't have that equation? That's weird. I should have had that. Oh, I do have it. So I just didn't see it. Does that make sense?
Yeah.
Good. Can I erase it, or do you want to keep it up? I can keep it up. It's fine. Okay, I'll keep it up. That's fine. Oh, I also suggest use a lot of colors. It helps me in my notes. I don't have any more notes with me. But you see, I use a whole bunch of colors. Oh no. I use a whole bunch of colors like blue, black, pencil, red. It highlights things that are important. So all the equations that I would write in notes in pencil, but then any equation or explanation, explanations where I wrote before, no force at this velocity, write that in black and write everything else in pencil. And then for your equations, just circle them in red, or put a box around them in red so they stand out. It makes it easier when you're trying to study. And for me, we had to create our own equation sheet, so it's easier to go back. But he gives you guys an equation sheet, so I can't find this question. I'm so annoyed. I really like to find this question. So I can show you
Is this from last year's?
what is
The equation, no, the question.
that I'm looking for. Yeah, this is from my exam, and it's very similar. It's just I can't find it, because I know I did it. But anyway, okay, yes, so that's that. So another equation for force that you can use is, okay, I'll just move down. Here's this. Another equation for force is F equals mv squared over r, where m is the mass of the particle, right? And so remember in class on the whiteboarding, he gave you the mass. That's where you would use this equation. Okay? And so you can use that equation along with the equation I gave above. And find, whatever it is you need to find, or something like that. So if you understand the equations, if you understand the concept of what V field does, then the equations become very easy to use, And so, just understanding the concept is the main thing. If you understand the concept, then you'll be fine. Any other questions? Because V field won't end here. You'll have to do them all the time now, especially when you get to torques and loops and all that, like your last exam stuff. V field will still be a part of that. So it's not like before, where it's like you just don't have to worry
So
about it.
B field is
Magnetic field.
field between magnets.
The B field is a field caused because of a current through a wire. So like in the lab, which you guys will probably do either whenever your lab is, I guess, but you'll see that you'll have a setup and you'll have a wire, but you won't turn on the current. So if you put the compass, it will point north. Okay. Once you turn on the current, then the compass will start going crazy. So in magnets, they're a little weird because there's no current passing through the magnet, but the properties of the metal itself create that field. But B fields are created when you pass currents through a wire. So my professor liked to ask that question, is like, what creates a B field? Passing a current through a wire. So I'm not sure if Professor Wadowski would ask something like that. I doubt it, but I'm just, it's good to know. Right? And so for a wire, okay, so you guys haven't gotten to the CIT. So I'm not going to do it, otherwise it's just going to confuse you.
What?
The B field from a wire to a point, you guys haven't done that yet. You guys have only done stuff like this.
Yeah.
So I'm not going to confuse you with that.
I'm so confused with the torque. The
Oh,
next,
yeah,
next chapter.
Yeah,
Oh,
I watched the pre-lecture videos.
yeah, okay, so torque is like, it's the rotation, right? It's the rotation of a loop because of a B field, again, okay? So B field will cause the rotation of a loop.
So that's the torque.
That's torque. Torque is how much, okay. Torque is how much force you apply on an object. Meaning, in a sense of rotational force. Meaning, if I take this expo thing, okay, if I pull it, that's just a force. That's a tension. If I push it, that's a compression. But if I go like, if I go like this, and I rotate my left hand towards me, my right hand the other way, that's a torque. Okay, it's going to essentially rotate this object. So a rotational force is called a torque. And torques are created from B fields. Like, and those torques, the changing the loop, well, that's later on, but that causes electricity and all that stuff. But
So how do
anyways,
you know which way the torque
will
occurs?
rotate
Yeah.
from the B field.
yeah.
So if the B field, I think, so the loop itself will have a current going through it. And
This is
yeah, so torque is mu cross P. Okay. So. Okay, I'm just gonna go very quickly because you guys haven't officially started this yet, but I'm just gonna clarify any questions you have. So let's say again you have a B field. It's easier to see. Okay. I'm going to do a 3D. Okay, and so let's say you have a B field going out of the page. Okay, and so let's say in this. Okay, so in the XY plane, okay, let's say you have a loop, right? You saw the loop, it looks something like this, right, in the pre-lecture video? Yeah, so this is called a loop, okay? And there's going to be a current flowing through the loop as well. Okay, either it's current this way, or this way, or whatever, right? And so the mu is the normal to the torque, the field, the loop. So like, let's say my loop is like this. Okay, off in that direction. Let's say this is at a 45-degree angle to the normal. Okay, well, it's drawn horribly. But let's make it like this.
So the mu vector is normal to B field?
No,
Oh.
the mu vector is the normal to the flat surface of the torque, of the loop.
to the flat surface. Okay.
I think so. Don't quote me on that. I'm pretty sure that's what it is. I have to see the drawing again. Yeah, but I believe that's what it was. Yeah, the mu vector, the mu is the normal to the, yeah.
How do you describe mu?
Mu will just be a number.
Oh.
Yeah. Yeah, it is the normal. I was right. The normal. Mu is the normal to your loop. Okay, so let's say you have a loop like this. Okay, and if we look at this from this face, okay, if we look at it top down, it looks like what you normally see. Right? Okay, so let's say this is 45 degrees. So your mu will be this. Right? So if you take mu with respect to the origin, it's going to be 135 degrees, correct?
Can you repeat that?
If you take mu with respect to the origin, it's going to be 135 degrees because it's 45 plus the 90. Yeah? So let me draw this out so it will be easier to see. Don't draw that one. This one will be easier to see because I did this. This is straight from my exam. So you have a B field going this way. A B field going this way. Okay, and your loop is this way. Okay, now when you look at it like that, you just have a loop, right? Now a loop can be a square, it can be that thing I showed you with the 2 prongs, whatever, it's just a loop. Okay? And you know this degree is 30 degrees. This angle. And you have your mu. Alright. So to find the mu, you have 30 degrees. 30 degrees over there. Okay? And then you have another 60 degrees to the y-axis, which is this way, straight up. But it's always 90 degrees to your loop. So your mu will be here. 30 degrees. So it's going to be 90 degrees to your right. So if you take what's mu, well, it'll be 30 plus 90, 120. Because your loop is 30, but your mu is 90 degrees to your loop.
It's like 130.
So 90 plus the 30 of your loop. So that's mu. So mu will also be given as a number. So mu cross B is then your torque. So let's go back to torque. Okay. So in this, the B field is going up. Okay, in this example, the B field is going up, and mu is this way, correct?
So do you also use the right-hand rule for this?
For this one, it's harder because there's so many angles.
Yeah.
So it's easier to just use mu B sine of the angle between them.
Sine of angle between.
Because you see, if you're trying to go like mu cross B, it gets really complex, right? So for cases like these where mu's are changing angles along with the loop, right? It's just easier to use sine of the angle between them. So mu B sine of the angle between them. That's just so much easier than trying to do, mu Yeah, you see what I'm saying? It's very hard.
Yeah.
Very, very hard. So just use the angle between them. But this is just simple. Let him explain in class properly and properly teach it. I'm just clarifying any confusion you may have. So that's the mu. It's 90 degrees. It's normal to your loop. And so when you cross it, okay, let's say this will start rotating. Let's say this will start rotating this way. There will be a point where mu faces directly parallel to B, right? Because it's going to go come straight down. At that point, you won't have that torque because sine is 0. Sine of 0 is 0, right? But because you have that current and because torque was already applied, it's already in rotation. So just one more angle up, and it's going to start rotating again. And so this rotation is what we use in like generators and shafts, right? He'll explain that. And I'm pretty sure he'll bring something to class or show you some nice pictures. Yeah. So this is what they use in a lot of things, like generators, shafts, things like that. They use loops and PHYS.
So you can determine the direction of torque by that thing, or the calculation?
Yeah. Well, you know it's going to spin, right? And now, given which direction it's going to spin is which way the current goes. Okay?
Oh, it's the same direction as the current?
No, it's going to be cross, the current cross B. But whenever you deal with the mu's and B fields and loops, they're just going to ask you what's the value of the torque, or what's the value of the mu, or what's the value of the B field, or whatever that.
Does the sign matter and stuff?
Sine?
Yeah,
What do you mean?
the torque. When you calculate, you get the number. And then you torque.
Like a negative torque? Yeah, I think it would be in the opposite direction. I'm not double sure, just asking in class, but I think that would just mean to the opposite direction. Than what you're assuming. So yeah, that's a crash. Let's let him like explain properly in class in case I'm messing anything up, right? But just to clarify whatever they might have confused you on in pre-lecture, that's the mu. That's torque. So you use torque a lot, and then you use it again for your final exam. When is your next exam?
After spinner?
29.
Oh, so like 2 weeks after spring break. Yeah. Let me see if that's not for 10 or something.
Next time.
Thank you. All right.
You have 4 problems for torque. Oh.
4 problems.
Yeah. Homework.
Have fun. That's not due, what, Friday?
Thursday.
Thursday night?
I spent 2 hours for my. Yeah. Oh, yeah.